Hi, in this video, we want to take a look at missing value patterns in R. Okay, so a missing value pattern is a data vector that record or data vectors, one or more, that indicates something about the missing value aspect of an observation. Okay, so why do we care? Why do we want this? Well, if I'm going to go through and I'm going to impute my missing values. So remember, imputation is where I have missing values in my data, and I basically go through and I make my best guess at what that value should be, or I put in like surrogate data, something of that nature, to improve my models. And it's pretty consistent. If you go through, you start building models with and without imputation, you'll find pretty quickly that for like predictive analytics, for a lot of situations, you want to impute. The exceptions are where you're going to be under scrutiny on your data, and things like hypothesis testing. Those cases, imputation is not a good choice. But if I'm doing predictive analytics, anything with machine learning, I probably want to do imputation. All right, well, after I go through and I impute, I insert values over the missing values, I lose a record of which values were missing and which values were not. Well, the missing value pattern records where and how the values were missing. So the first thing that this does for me is that this gives me insight into subpopulations. So I can be looking through the data. If I look at my missing value patterns, at a time, if there was a change in how the data was recorded, or maybe a particular employee was skipping over some stuff, I can see that in the missing value patterns. If I don't have it, I can't spot it. So I can detect subpopulations and other aspects of the data that I wouldn't see otherwise. Also, these can be very useful predictors. Usually they're not very good by themselves, but if I put them in on top of the regular predictors that we're imputing, a lot of times we can get a lot more oomph in our model. Another reason for it is that by including these vectors on there, we can like compensate. If we did like poor imputation, having that other vector over there to indicate what's going on, it can sometimes shift off from the mistakes that we made in our imputation process. Maybe not mistake, but maybe we did things not the best way possible. And because there is a difference in the subpopulations that we really won't know until it's too late. And the missing value pattern can compensate for the bias that we've introduced. Now, I have not found a good package in R for this yet. Good package, in my opinion. There are some packages that will do this for us. The one that I've taken a look at is the NIAR package. I'm going to pronounce that as NIAR. That's not how you say it. I can't really find a good English pronunciation of that. But what it does, it creates something it calls a shadow matrix. I don't really like the shadow matrix because it's really the same information as the binary missing value patterns that I build with zeros and ones, but they're character vectors, and I just find it's just not, even though it's easier to interpret and look at as a human for the purpose of like machine learning, predictive analytics, I don't think it's the best way to go. I think a straight dummy variable binary vector is the better way to go. So I'm going to do everything manually. Conceptually, you could go over to the NAIR package and use that. The NAIR package does support a lot of things very nicely. It'll be very easy. Here, I'm doing everything manually just because it's more of the base R way. And I just feel like the other packages, the other options I've found in R are not really shortcutting the work worth it enough to even to mess with another package. All right, so let's do an example. I'm going to take the Nashville housing data set from Kaggle, and that has a good number of missing values throughout. And then we're going to just kind of go through some process of building missing value patterns. So here I'm loading the data using the read-R version of read CSV. Remember that for call types, I need to specify each one. And here I'm calling, if it's a number, it's numeric. If it's a factor or a character, I say it's a character. And if it's a date, I put a D. All right, and here what I'm doing, I'm cleaning up the names from how they appear originally. I'm just doing a little bit of string manipulation, so it's a little bit easier for human beings to look at it. Now here I go through and I sort the columns and the rows by the number of missing values. I find that this is a good thing to do before I do imputations, just so I can get a feel for what's going on. It makes it easier to spot redundancies in the missing value patterns later on also. Having the columns sorted by the missing value patterns is a good practice for imputation, which I cover in another video. If I am working in a big data project where computation time is an issue, I will not be performing this step over here. I would just run as is because it's just not worth the computation time to sort. All right, so let's go ahead and take a look at some stuff. So here, I just go ahead and take, what's the class of my variables? Well, I've got 16 characters, 1 date, 11 numeric. All right. Why is that important for this? Well, if I'm going to be imputing, how I impute numeric variables and how I impute character variables are very different. Now, dates I would have to take a look at individually, because it might be there's only a few dates. And so in that case, I want to treat it like a possibly like an ordinal value, just because, like, if there were only, like, let's say 5 in a large data set, then I want to pick one of those 5 more than likely. But if there's a whole range of them and I want to impute the date, then I want to treat it more like a numeric. So you have to take a look and make a decision. All right, so now let's go ahead and look at the number of missing values in individual rows. And so we can see, first off, there's only 2 observations that have 0 missing values. So let's think about that for a moment. If I was to use this data set and I was to omit observations that were missing 1 or more values, I would only have 2 observations left. That wouldn't be good, right? I would lose a lot of data. Now, if I'm willing to tolerate just 1 missing value, then I've got a large portion of my data is preserved. But we can see that almost 25,000 observations have 19 or more missing values. So I need to like, missing values is a serious aspect to this particular data set. Now let's go ahead and take a look at the columns. All right, when I look at the columns, there are 7 columns with 0 missing values. There are 2 columns with only 159 missing values, and then it kind of gets spread out. We can see over here that there's one that has like a lot of missing values in there. That's going to end up being like a suite, condo, apartment number, which that makes sense, because if it's a house, it's not going to have a suite or apartment number. All right, so now let's go ahead and actually start looking at missing value patterns. When I talk about missing value patterns, I have some options. So the first one is I don't do it at all. Now, if you're not going to do it at all, then you're probably not interested in this video, so I'm not going to talk about it too much. But that is an option. There are times that, like if the missing value pattern just isn't a useful vector, don't use it. The most simple option that involves MVPs is that we take a single binary missing value pattern. So here, this vector indicates a 1 if there is 1 or more missing values in the entire row. So 1 or more. So if I look up here in my data set, only 2 have 0 missing values on the rows. Only 2 rows have no missing values. All right, well, in this situation, only 2 of the rows would have 0. Everyone else would have a 1. I mean, that's nearly a constant vector. That's really not going to be an informative vector, but that is an option to work with. So if I have 1 or more missing values, I have a 0, 1 vector indicating it. Now the count here we create a vector that counts the number of missing values. Okay. And then here, I'm going to call this the unique option. Every single unique, so I go through each of my predictors. I make a binary dummy variable that indicates if there is missingness or not on that individual vector. And then I go through, and every single predictor gets a binary vector, and I go through and I remove the redundant columns. So if a column repeats itself, I get rid of the repetitions. And I call this the unique missing value pattern option. Now with single missing value patterns, this is a good choice when the ratio of observations to predictors is small. So if I have nearly as many if I have nearly as many predictors as I have observations, I really don't want to be generating new predictor variables if I'm doing something like linear regression. So I'm going to want to shy away from having like a whole bunch of different missing value patterns. So the unique option would be a bad choice in this situation. Here I'm only feature engineering one predictor, so it's a conservative choice. It's a good way to go. Now if my count missing values are highly skewed, or there's like just something not right about it, I don't like it, it's not performing well, I could go in with the binary option. Sometimes getting the unique missing value patterns is computationally unfeasible. Like the situation where I have like big data, and like my machine just can't handle what's going on. My machine's getting choked out by what I've got. I don't want to be generating a whole bunch of vectors. So one thing to remember when I do predictive analytics, when I do machine learning, the more predictor variables I have, the more prone to overfitting I am. Always keep that in mind. So if I'm generating a whole bunch of unique missing value patterns, a whole bunch of them, then I'm making myself more prone to overfitting. The single binary and the count version are good choices if I'm worried about creating vectors that'll create an overfitting situation. Another reason why we would want the binary version is if the missing value patterns are highly correlated. That's not the correct word. Concordant is the correct word, but conceptually, if they end up being correlated, then I don't want to have a bunch of correlated vectors running around. I just want one representation. Now, this will be a poor choice when the resulting binary vector is nearly constant or it is constant. And if the unique missing value patterns are not concordant, they're not correlated with each other, then I'm suffering a pretty big information loss. So, it's just something to take a look at. All right, so let's go ahead and take the national data set and let's do the binary missing value pattern and take a look at what we get. All right, so here I'm using the apply function on the rows. So remember, on margin equals 1, that says do it on the rows. If margin is equal to 2, it's doing it on the columns. So I'm taking the missing value, I'm making it a 0 or a 1 with the as numeric function, and then I'm taking the maximum along the entire row. So if there is one missing value anywhere in the row, this vector will be a 1. If there are no missing values at all in the entire row, then it's going to be a goose egg 0. So what do we get? Well, we see that there are only 2 observations with no missing values, and there are over 56,000 with 1 or more. This is nearly a constant vector. This is really not going to be informative. So I really, in this situation, for this data set, I would not want to use this vector as a predictor. And here, let's go ahead and take a look at the histogram. We can see that proportionately, over 56,000 over here, and then there's 2. It's so small, it looks like 0. I probably should have used like a bar plot instead of histogram, but I hope you guys get the information. All right, now the next option we can go with is here, instead of doing a binary yes or no, we can actually take the count of missing values. And I found that this is usually a better way to go. But there's a catch. If I do the count of the raw missing values without considering unique patterns or not, then my numbers can get inflated kind of artificially, and it may or may not give me a good predictor. So when is this a good choice? This is a good choice when my ratio of observations to predictors is small. So here I have the number of observations just a little bit bigger than the number of predictors. And so in that situation, I don't want to be doing a lot of feature engineering, creating new predictor variables. If my binary vector is nearly constant, like in this situation, if I'm in a big data situation where my machine just gets choked out from trying to compute the missing value patterns, then this is a good alternative. Or when my unique missing value patterns are nearly equal to each other, they're highly concordant, highly correlated. Now, this is a poor choice when the count ends up giving us a poor vector as a predictor, or when we have non-concordant unique missing value patterns. In that situation, I'm suffering a big information loss by going with just one vector instead of the whole kit and caboodle. Now, something to be mindful of is if I have redundant missing value patterns like we have in this data set, which I know because I've already looked at it, then we should remove the redundant patterns, then take the counts, usually. And so after I do this, we can see the counts, which we've actually already looked at, but we can kind of get a feel of the vector. And we can look at the histogram. Whoops. And so we have a bunch of, low numbers, those like 1 or 2, the vast, a good number here. Then there's a few floating around 10, and then a few around 20, or actually a good number around 20. Okay. Now let's take a look at the unique missing value patterns. So what we're doing here is that each individual predictor, we are looking at its missing values, and then I'm creating a binary vector that indicates was there missingness on this observation or not. Now, after I get all of these binary vectors, I'm going to go through, I'm going to remove the ones that are constant, and I'm going to remove the ones that are redundant. Two things. All right, now this is going to be a poor choice when my number of observations is just a little bit more than my predictors. And remember, whenever I'm doing feature engineering, the more predictors I have, the more prone to overfitting I am. So if I do this and if I create a whole bunch of predictor variables, and this could be one of the ways that we do it, I'm making myself more prone to overfitting. So I always have to watch out for that. If the missing value patterns are highly concordant or constant, highly correlated, then there's redundant information in there, and it's just not worth it to lose the computation time when I'm doing my model fitting. And when we do this, we have to worry about computation time if I'm dealing with big data, because my machine can just see it choked out. All right, so what I'm going to do, I'm going to go through each individual column. I'm going to look at its missingness, I guess, if that's a word. And then I'm going to convert. So this is a true false output. And if it is missing, it's true. If it's not missing, it's false. And then as numeric, we'll convert it to 0 or 1. Okay. Well, if I have a constant vector of either no missing values or a constant vector of all missing values, then I don't want that in my predictors, right? There's no information there. If all of them are missing, I shouldn't even have the vector in there. If none of them are missing, then the missing value pattern isn't informative. So here, I'm making a logical statement of, is the average 0 or 1? If it's perfectly 0 or perfectly 1, then it's a constant. So I'm just throwing it out. Now on this step, what I'm doing is I haven't found a faster way to do this in R. So I want to use the unique function. Now normally the unique function goes by rows. It doesn't go by columns. So what I do here, I take the transpose, which makes rows into columns, columns into rows. So my data is like this. I've got a bunch of columns. I take the transpose and it tilts it like this. I take the unique, that removes the redundancies, and then I switch it back like this. All right, my hands can't technically make the correct motions for transpose, but conceptually this agree with me. And now here, so I can see, and this is something that I do. If in machine learning, this isn't going to be very, like the algorithm doesn't care what you call it. But for the purpose of humans interpreting and understanding the missingness in your data, this is a good idea. What this chunk of code does, this goes through and this takes the name of all of the vectors that have that missing value pattern and puts it onto the missing value pattern. So we can see that property address and property city columns have the same missing value pattern. We can see that address, city, tax district, acreage, neighborhood, land value, building value, total value all have the same missing value pattern. Image has its own, owner name has its own, full bath has its own. Now exterior wall, grade, year built all have their own, all have the same missing value pattern, and we can go down. Now, since I sorted the columns by the missing value pattern counts, I know that here, these have the fewest missing values, and suite condo has the most. That's going to be the number of the suite, of the condo, the apartment, etc. Now, after I've been working through this, in R, this is not actually a data frame. And so this step is just going through and just making it into a data frame so I can use it the way I want to. Now let's take a look at the dimensions. If I take a look at the dimensions before I did the unique step, I can see that there were 21 binary vectors. All right, after I got rid of the redundancies, that's 11. All right, so if you think about it, if I was to use this raw without getting rid of the redundancies, I would have 10 vectors I would be throwing into my model computation that are completely useless. They provide no additional information. Okay, now if you think about what I've done in this code so far, when I took the counts, I made no consideration of the redundancies in the missing value patterns. So now what I want to do, I want to get the counts after I've removed the redundant patterns, because what I'm going to see in a moment off of the histogram that's at the bottom is that there's patterns in the missing values, so that if this column is a missing value, this column is also, and this one is also. And so because of that, the numbers can get inflated and I can lose informative value on the counts. So after I reduce it down, we can see that there's a great reduction in what's going on. It went from, the maximum was like 21, now it's 11. All right, that's a big change. And so if I look here, this is the histogram of the counts. Let's look at what we had before we removed the redundancies. All right, so it looks like the ones that previously were floating around 20 are now floating around 10. So everything got pulled in. And this will probably improve the predictor variable. Don't know for certain. You don't know until you try, but I would anticipate that this is the better version of the count to use. All right, so to sum it up, recap. When I have missing values, I'm going to go through and I'm going to impute the values if it's appropriate for my problem. Impute means I fill in the blanks with basically my best guess. Well, I might have made a poor choice. Maybe there's aspects of the different recordings of the data that there's something in the subpopulation that I'm not aware of. to try and protect myself from making a mistake, I'm going to include binary vectors or count vectors indicating missingness in the data. All right, my options are: don't use missing value patterns, use a binary vector recording if there is one or more missing values, use counts of the number of missing values in the row, or to go with unique missing value patterns. Here I have a whole bunch of binary vectors. And anything I can generate with binary vectors, I could also choose. Most of the time, in my experience, it's the unique missing value patterns are the most common. Well, that's all I've got for you. Take care and goodbye.